Periodic signals. A periodic continuous time signal x of t has the property that there is positive value of t for which x of t continuous time signal has the property that there is positive value of t for which for all values of t for all values of t. In other words, a periodic signal has the property that it is unchanged by a time shift of t. Unchanged. In this case, we say that x of t is periodic with period t. Periodic continuous time signals arise in a variety of contexts. For example, as illustrated in problem 2.61, the natural response of systems in which energy is conserved, such as ideal LC circuits, without resistive energy dissipation, and ideal mechanical systems without fractional losses, and are periodic and in fact are composed of some of the basic periodic signals that we will introduce in another section. Here, continuous time periodic signals. Continuous time periodic signals. Continuous time periodic signals x of t. Here x of t is like this. Here x of t while t equal to 0. Here x of t while t equal to t. This t equal to t x of t here while 2t same. Periodic, continuous periodic signal. Same. What is same here? Same. Same. But this period here in between here center minus 2t minus 2t to minus t. Here to there minus t to 0. 0 to plus t to plus 2t. So same coming periodically. That's why continuous periodic signal. Continuously coming. Same like. An example of a periodic continuous time signal is given in figure 1.4 from the figure or from equation 1.11, that is x of t equal to x of small t plus capital T. This is for periodic, capital T. This is for time in x-axis. This t, small t, cap t, period. We can readily deduce that if x of t is periodic, x of t is periodic with period t, with period t, all of t, then x of t equal to x of t plus mt plus here m will come. The for all t, for all t, for all t, for all t, okay, for all t, this one. For any integer m, for any integer m, thus x of t is also periodic. X of t also periodic. That x of t also periodic with the period 2t, 3t, 4t. X of t is also periodic with 2t, 3t from here and 4t and so on. The fundamental period t naught, these all are t naught. T naught of x of t is the smallest positive value of t, smallest positive value of t, here minus 2t, minus t, 0, t, 2t, 3t. So positive value of t, for which equation 1.1, 1.1 volts, so small t, positive. Okay. This definition of the fundamental period works except if x of t is a constant. The definition of the fundamental period works except if x of t is a constant. The definition of the fundamental period works when it will work. Except if the x of t is constant. Except if constant means it is not to be a constant, regular, then only it will be work. The fundamental period will work. Otherwise, if constant means it will not periodic will come. In this case, the fundamental period undefined. The fundamental period undefined, like this going on. So since x of t is a periodic for any choice of t, since x of t is periodic for any choice t, so there is no smallest positive value. A signal x of t that is not periodic, x of t is not a periodic, will be referred to as an aperiodic signal. If it is not periodic, it is means aperiodic. It is not same like this, periodically same continuous to be come then only periodic. Otherwise, it will be aperiodic signal. Then periodic signals are defined analogously in discrete time. Periodic signals are defined analogously discrete time. Here continuous time means a continuously coming. Before also is there. Continuous, that's why continuous time. Then periodically coming. Periodically. Here one period, same, here, same. Particular time. That's a periodic signal. Okay. In periodic signals are defined analogically in discrete time. Specifically, a discrete time signal x of n is a periodic with period n, where n is a positive integer. N is a positive integer if it is unchanged by time shift of n, that is if unchanged by time, x of n equal to x of n plus capital N. Capital N. For x of n equal to x of n plus capital N for all values of n, if equation x of n equal to x of n plus 1, n plus small n capital holds, then x of n is also periodic. X of n is also periodic with period with period 2n, 3n, and so on. The fundamental period n naught, is the smallest positive value. So, smallest positive for n, for which equation 1.12 volts. An example discrete time period signal with the fundamental period n naught equal to 3 as shown in figure. A discrete time period signal, this is the discrete, not continuously. So, like this. So, discrete time signal with the fundamental period n naught equal to 3. Once again, if equation 1.12 x of n equal to x of small n plus capital N holds, then x of n is also periodic with period, which is 2n, 3n, and so on. The fundamental period n naught, the fundamental period n naught is the smallest positive value of n, for which equation 1.12 holds an example of a discrete time period signals with a fundamental period n naught. Discrete time period signals. Here, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. That's why n naught is 3. Okay, this one. Done. Same. Come. Okay, and then here. Yeah. This one also same. Okay, so 3. Then here equal distance, equal time period. Okay, equal time. So shown in here. So that's why discrete time period signal, with the fundamental period is n equal to 3. This is 1, 2, 3. Fundamental period is 3. Okay, like example 1.4. For this example 1.4, this figure, the signal x of t considered in example 1.4. Here x of t, that is in 0, before 0, that is in left side, the negative side, minus 6 pi to 4 pi minus 2 pi, like this. Here from 0 to 2 pi, 4 pi, and so on, t at that time, t. Here let us illustrate the problem of solving may be required determining whether or not a given signal is periodic. It is periodic or not periodic. We have to find the signal whose periodicity we wish to check is given by, we have to check by this one. X of t equal to cos t. That the condition is if t is less than 0, then cos t. If t is equal or greater than 0, then sin t. Here. So from trigonometry, we know that cos of t plus 2 pi equal to cos t. Sin t plus 2 pi is sin t. Thus, considering t is greater than 0, this one, and t is less than 0 separately, we see that x of t does repeat itself. X of t here repeat itself over every interval length 2 pi. That is, for example, here same, here same, here also same, like this. Here 2, we can check from here also. For example, 4 by this, we take this one only. Okay, like this. Then same here, then same here. Okay, this period is 2 by, okay, but here what we have started, here end, here so here it is different. That's why here, yeah, x of t also has a discontinuity at the time of origin. This origin, so does not recur any other time over time. Actually, this period is 2 pi only. Period is 2 pi. Here finish, then here finish, then here finish. Then like that, it is not a periodic because it must recur periodically. So